Hello, my name is Reda, and I'm very happy to be presenting this work on rainbow color maps. What are they good and bad for? Now, color is a well-researched area in data visualization, and the topic of rainbow color maps have been much discussed both in the VIS community and in other disciplines as well. And there's general agreement that while rainbows can be seen as aesthetically pleasing, they should be entirely avoided in visualizations. And this is based on a lot of research that demonstrate problems when people try to interpret rainbow color maps. On the other hand, if we look at visualization practice, we see a constant stream of rainbows. And it's almost like no amount of discouragement seems to stop people and designers from using rainbow color maps in the wild. Now, this gap may be problematic on a number of points, but it's also interesting from a visualization research point of view. Do practitioners know something that we don't about rainbows? A closer look at the empirical visualization studies suggests also mixed results. Some studies, in fact, show rainbows to be superior in some cases, and other studies show the complete opposite, suggest that the use of rainbow in visualization is highly problematic and should really end. Which raises another question: what could be driving these inconsistencies in findings? One answer is it's simply a matter of task. Different studies have utilized a variety of tasks, like comparing models or making medical diagnoses, so it's conceivable that people might be able to do better with a rainbow color map under certain conditions. But this explanation is not really satisfying, because it doesn't tell us what's in a task that makes it more or less suited for a particular color map. And more importantly, without an explanation, there's no way of predicting if a new unseen task might work better with a rainbow color map or with something else entirely. So instead of task, we're proposing a feature-level account of color map utility. This is based on a conjecture that different color maps will highlight different things in data. So given a data set, we might see one kind of feature if we use a color map A, but if we switch to a different color map B, we might be able to see entirely different sets of features altogether. And it's quite possible that we can't see both A and B at the same time, meaning that there is a trade-off associated with using different color maps in terms of which feature they highlight or emphasize or de-emphasize in the data for that matter. And this is the hypothesis that we think explains why rainbow color maps can be both useful in certain conditions and also potentially problematic in others. Specifically, when looking at colorful visualizations, we tend to see distributional features in the data more clearly. So for example, in this rainbow visualization, I can see distinct colors like red, blue, yellow, and associate these colors with hotspots or valleys in the data. And this is not specific to rainbows. In fact, even with a colorful perceptual color map, we're still able to see features and refer to them by their color names, just perhaps to a lesser extent than with a rainbow. But this enhancement does come at a cost, in the sense that we might miss other features in the data. For example, when looking at this visualization, which is decidedly less colorful, we start to recognize other features that were not clearly visible, such as these bean-shaped forms. Notice how it's much more difficult to see these shapes in a more colorful visualization. It's almost as if these colors are crowding out these local features. I'm calling these quote-unquote local features because they are defined by a small local perturbation in the density. And interestingly, this modulation is not specific to rainbows. Instead, we hypothesize that this is a gradual attentional bias towards one kind of feature over the other, largely explained by how colorful the visualization is. So how do we test this hypothesis empirically? In prior work, we've used a lineup test to evaluate the sensitivity of different color maps. We showed participants a lineup of visualizations and asked them to select the one that looks different. Here, that would be this visualization because unlike the other ones, it has smaller bean on the left. With this test, we can measure the sensitivity towards one feature type. But how do we test the competition on attention between two features? One idea is to add another set of visualizations to the lineup, one of which is this time is different in its density. So we have a lineup that conveys two competing signals, a target that is different in its local features, and another target that is distinct in its distribution. And with this setup, we can see if viewers are biased to select one class of feature over the other, depending on the color map. In effect, by testing different color maps, we can measure if people are biased to report one of the two targets over the other. So according to our hypothesis, we would expect that participants will be reporting more local targets when the visualization is less colorful. In other words, we expect to see attentional bias towards local features. Conversely, when we use a more colorful design, we would expect to see a high percentage of global targets. Those are the targets that vary in their underlying distribution. Let's look at the results. The diamonds here show the observed average bias for each color map, and we can see that the pattern is in line with our hypothesis, even though the bias for local features is less than what we had expected. Now, looking at the full range of responses among participants, we can see almost equal attention to local and global features with sequential color maps, like with VIS and with this single hue blue color map, both of which have a limited amount of hue variation. By contrast, with a rainbow and a colorful diverging color map, we see a clear bias for the global distributional features that we have in the data. Overall, the level of bias is quite predictable based on how colorful the visualization is. We can also look at the overall sensitivity of the task, which is to say detecting either of the two targets. And here, somewhat surprisingly, we see better overall sensitivity with the more colorful designs, with rainbow color maps in particular performing the best here. That said, the overall sensitivity does hide variation in target selection among the different color maps, as we saw earlier. And a better way of looking at color map utility is to really investigate which kind of target they bias participants to focus onto. So the takeaways are that when people look at rainbows or some other colorful design, they are more likely to notice global features in the data. This is quite useful to draw attention to things like distributions, hotspots, and even implicit contours. On the other hand, when looking at a less colorful visualization, people will probably favor focusing on local features. This includes shapes and outlines and other features that are defined by local differences in the data. Perhaps a more important takeaway is that there were no good or bad color maps, at least in this study. Instead, all designs we tested were useful and afforded varying level of attention to different classes of features. So instead of a simple dichotomous framework of good versus bad color maps or perceptual versus non-perceptual designs, we suggest looking at the attentional benefits and costs associated with using different color encodings. This is to say that different color maps will highlight different features in the data, and the best choice of color encoding really depends on one's need, more than it depends on inherent perceptual qualities in the color map itself. Now, what if we want to communicate multiple feature types at once with a dataset? A simple answer is perhaps redundantly encode that data twice in two separate color maps. We test this setup in a separate study, and we find really interesting results here. So if you're curious, please consult the paper. And with that, I would like to thank you for your attention.